5, 4, 3, 2, 1. Engines full power and liftoff.
We care about this part.
Where'd the
I
rocket
hooked up the
go?
igniter. Once again, shout out to being hands-free with this chest cam, and we were ready to send it.
5, 4, 3, 2, 1, 0.
Here, I'll just mute it. But this rocket, like, it's two stages. Pew! And they like the cameras are meant to deploy out to like look down,
Okay.
and they deploy while all going Mach 3. Yeah, and that kind of
It don't do too good going
that
Mach
kind of
3.
yeah, that kind of yeah, they kind of threw off the center of pressure, and it became a corkscrew. It was pretty sweet though.
Dude, BPS.Space is so cool.
I know. I want to build rockets like he does. Like he uploads like every 3 days.
I don't know how.
He literally builds a rocket that like the same class of rocket that Star is doing, but he builds it in a week.
It's ridiculous. It's crazy. Is that his full-time job? Is
Yeah.
this what he does for a living? Yeah.
Yeah, that'd be pretty sweet.
That would be pretty cool.
Though I don't have a CNC in my garage, so I can't really mimic him.
Not yet.
But Elko, hear me out.
Elko is my garage.
I live in Elko. But it is facts. I actually have been trying to learn how to create like avionics and GPSs and stuff. Because as a mechanical engineer, I
don't see that side so much.
No, I haven't been taught a single thing. Like even like for first year, did you take any Arduino lessons?
No.
No? So where I took my first year, the first year computer science class,
Yeah, like
or
the
engine
comp.
I took with a lab, and the lab was Arduino.
Oh, that's actually sick.
And so like I think the most complicated thing we had to do was like make a LED mimic like flickering of a campfire.
Oh, that's not bad.
But I still learned how to turn it on at least.
It's just a start.
It's a start.
Did you guys do Python or MATLAB?
MATLAB in the lectures, but then C for Arduino.
Yeah, right.
But like MATLAB is like written in like kind of like C.
Dude, MATLAB is everything. It is Python, C, Ruby.
Yeah.
It's got a little bit of everything.
And you know what? It doesn't deserve the hate it gets.
Honestly, I do like it. I have used it for some of the imaging stuff that I'm doing, and it comes in handy.
So like using MATLAB instead of learning Python?
I have a Python background.
Oh.
But it's like MATLAB outputs it really nicely in these figures. So I'm just going to do it this way instead. Because you can do matplot.lib in Python, but I don't know. I just like the MATLAB output better.
I'm the complete opposite. I'd rather use matplotlib than MATLAB.
Really?
I don't know why. I'm just not good with MATLAB. Like I understand it, but like matplotlib, it's like I can get these beautiful
very
formatted
intuitive
figures.
Yeah.
But like, what kind of why'd you need to use MATLAB for imaging?
So standard camera uses a Bayer matrix. Bayer matrix is 25% red pixels, 50% green, and 25% blue. So you're able. It uses this thing called demosaicing, and there's a couple different algorithms, but to account for having less pixels per color, the like average across an area to get like a full color image. So you have RGB values for every pixel, rather than like, only 50% of these pixels are green. No, you can average across and figure out the rough estimate of the values. Like your eyes aren't guessing, but like any camera is guessing.
Right. Yeah.
Except for film. Film is not guessing. Film is crazy.
So you're just filling in, like, so you're splitting into its 3 parts, but one part's 50%. And then filling in the gaps from that separation with the nearby average values.
So most camera modules actually do that for you. So you actually have to go in and reverse that most times. If you can't get the .raw file, that's the raw sensor data, you have to remosaic and break it up. So I've been working with one of our advisors on making a Python script for that. And it works pretty good. I just have to adjust it a little bit for when we have a near-infrared filter on it to allow us to get our target 3 bands for our multispectral imager.
Interesting. And then with these 3 images that are produced, like what will kind of be the step for each? Like, why would we want the red image and the green image and the blue image that's measuring near? Like, what would each purpose be?
On their own, they're not much use, but when you subtract them, like every picture is reflectance values.
Right.
Right? So the red picture is just your red reflectance values.
Yeah.
So you can take your red and your infrared, and you can add them, and then on the bottom you divide them and subtract them, and then you can multiply that by 100 and you get a percentage, or you can leave it as a ratio or like a decimal value, and that tells you like the vegetation reflectance in the area. So like everything absorbs different wavelengths. So trees, they reflect green. So they show high red values, right?
They reflect green, so they'd show high green values?
Yes, high green values.
I'm like, damn.
Dude, those trees, they're red, man. Yeah, sorry. Long day.
I can see that. Okay, yeah. And so you get the red reflectance, the green reflectance, and blue reflectance. In this case, it's near.
Yeah.
We're not measuring blue. Or we have a triple band pass filter.
Not confirmed, but
that's the goal.
That's the goal, is to have three bands on one light path.
A triple band pass filter, which will only let in red, green, and near.
Yeah.
And then the near will be measured on the blue pixels, and then you can subtract the near from the other pixels to get red, green, and then near independently.
That's the idea. Yeah.
And then with those values, I don't know how much you want to talk about NVDSI?
NDSI is normalized difference snow index. So that's just, it shows what areas have snow and what don't. It's putting a color map over a subtracted reflectance.
Oh, okay.
Thing. It's not like, I'm trying to think of the words to describe it in a clear and concise way, but it's, yes, the process of getting those images are complicated, but the post-processing is a little less complicated in that aspect. It's just subtraction, and there's a lot of stuff that comes up before you do like all that end work stuff of subtracting it. You have to do all the post-processing of like super resolution, making sure that it's like in focus and the pictures you're getting are the expected pictures that you want. And there's ways of simulating that and, making sure that it works prior to sending it up into space.
I remember something from your GAM presentation where it was an emittance over a certain threshold would be classified as snow using red. Or
yes.
I believe so. And similarly for the ice index and what was the other index?
So there's normalized difference water index, so differentiating between land and water. Normalized difference snow index, which we talked about, and normalized difference vegetation index that maps vegetation. Red is really useful for ice measuring and differentiating like impurities in snow and ice.
Okay.
And green and SWIR are good for just normalized difference snow index. Like that's bare minimum, like what we'd get out of our mission is normalized difference snow index. And you can do all of these like indices using like, let's say that you want to measure NDSI. That's normally green and SWIR. You can use red. It's just not going to be as accurate. It's going to be significantly less accurate.
Interesting. Okay. And so, like for our mission, it is snow imaging, Arctic imaging is what I think we're calling it, but it's mostly snow.
So our primary focus is, I believe, is NDSI is what we're focusing on.
And including NDWI and NDVI.
It just helps discriminate and get better data product for clients.
Okay.
It's the addition of the 3 bands or I guess another 2 bands. A 2-band system is bare minimum.
Yes.
A 4-band system in our case is ideal for us. So fingers crossed that we get better data because we have 4. Like when we fly 4, we're going to get better data.
Right. And then there's a different complexity that comes with having 4 bands. Well, I mean, I guess it's more of a cost complexity.
Well, there's the filtering issues that we've talked about before, like $50K US for a little piece of glass that filters. And then there's my proposed idea, but if that doesn't work, then we're down to a 2-band system.
Which, yeah.
It's not ideal, but it gives us, a chance to figure out what we're doing now with we're not as mature as a team as before. Elliot and Liam are
alumni now.
Alumni and literally probably the smartest people on Iris.
It's actually weird. Like the Nick always calls them his generation, but like the previous generation of Alberta Set members.
Nick is not part of that generation.
I don't know why he says he is, but because he's been around a long time. But he joined in high school.
Nick, yes, he is part of that Alberta Set generation, but he joined like when they were, I don't know. Like, yes, he is a part of it, but also he's a part of our generation of Alberta Sat too.
Yeah, but it's like that generation had it all figured out. They knew how to build satellites.
And then we're sitting here. Well, I don't know. I feel like the full times we're learning a lot.
Like we're gonna get it done, but it's like we don't have. I mean, they probably felt this way when they started.
I think it's just a matter of getting the ball rolling.
Yeah,
and then we can go from there. Speaking of getting the ball rolling, we're getting pretty close to launch for CanRGX, so we would like to do some shake tests on the shaker table on some of our joints. Is that something you could help us with?
Well, I'll start with what you put in you tagged me in on the Slack.
Oh, yes.
That you didn't respond to my comment.
I didn't see your comment.
No. Did your random vibration testing just assume that the bottom of the structure was completely fixed in the Pelican case?
Yeah, because it will be.
Oh, it will be? How?
Well, not completely fixed. It's not going to be welded. It's going to have like a bunch of...
Okay.
But you can assume that it's pretty much fixed.
Okay. That was my one question. I was like, it looks like he just glued the bottom down.
Yeah, it's going to be like bolted from the bottom. Because we have a metal plate that goes in there.
Right.
And then that gets not melted. It's in there for good now. Good luck with that. No, it's bolted in each 4 corners.
Right.
To keep it in place. So
essentially fixed.
I assumed that it would be fixed.
I don't think it changed that much, like doing pin supports at the bottom.
It's because you're not like you take away your rotation, you take away lateral, vertical, longitudinal. It's fixed.
Yeah. Okay. Yeah. Okay. Well, for testing, I don't think it's going to fit. The Pelican case will fit.
No, we're not going to test. I just want to test a couple joints. So we're going to get some aluminum extrusions and then put some of the L brackets.
Okay.
And then we're going to shake that is my idea.
It would also be good to shake all your harnesses. I can actually send you, I have like a document from the CSA kind of outlining what they do to like
verify.
not verify, but how they break down their shaker tests.
Okay.
So they usually will like start with a constant frequency to ensure that everything's put together. So like if you put it on 50 hertz and a bunch of screws start falling out,
You got a problem.
yeah, so you go back to stage 0. So yeah, they'll start with that, and then they will do a random vibration test outlined by a PSD plot. So that's a power spectral density plot, and that basically denotes the average power at each frequency that makes up the signal. And so for
Okay.
like Fourier series, basically, like the theory behind that says you can break any signal down into a sum of sines and cosines at varying frequencies. And what a PSD plot is basically, it's showing the relative amplitude or power of those different frequency components. So like maybe during flight, for some reason, 50 kilohertz has a lot higher, like more power at 50 kilohertz
Right.
than like 30 kilohertz. So that would be more of a part in your shaking test that you'd want to like be careful
Focus,
about,
yeah.
because that's where most of the energy will be added in. But yeah, I can send you that.
That'd be cool. Yeah.
Do you have a PSD plot? I think
Yep.
you do.
I
Yeah.
do. I have vertical, lateral, and longitudinal.
Are they very different?
They're relatively the same.
Because for Xalta 2,
Yeah.
we were just given one.
They're pretty much the same
Yeah. And so
across.
we
they
just
they like
assumed-
they peak at roughly the same spot. So
Oh, yours is... Oh, like you actually have like accelerometer data from...
yeah,
Oh, okay. Like the PSD plot we're given is like very crude.
you should see ours. Ours is very good.
Okay.
It is much better.
Well,
I'll pull it up for you here. And I can
as soon
show
as
you.
my smooth brain figures out how to do inverse Fourier transforms, we can test.
That would be very cool.
Well, and we need to figure out how to fix it to the shaker table.
what's the weight limit's like? What, 5 pounds? Upper.
Everyone says it's 5 pounds. It probably is around 5 pounds. The only, like, it can shake pretty theoretically anything. The only thing that changes is the amplitude. You put 100 pounds on it, and you just will
Right.
have a really reduced amplitude.
That makes sense.
But no, yeah. So for a Falcon 9 launch, the PSD is only given for, I don't know, it's undirectional. It's just provided. So for Xalta 2, we just assumed it was equivalent in all directions.
I mean, if you look at ours, it's
Oh, wow.
it's pretty well put out, but it like the highest peak is always around like 138.
Do you have
hertz.
that in like a CSV?
Nope, but I have this software that you can input the graph into, and then you can like manually put like the zeros and then the upper limits, and then you can like go along and plot each point,
Okay. So that
and then we can get that data.
We
Yeah,
can get that into MATLAB.
yeah,
Because we will use MATLAB to do the inverse fast Fourier transform.
yeah. I'm not doing that by hand.
I wouldn't either. Right. So you have a random vibration testing outlined by a PSD provided for like launch conditions or flight conditions. And that is probably going to be the as close as possible case to what you're...
Actually, going to experience.
Yes. But there are other tests you can do, like a swept test. So you
What's
can
that?
sweep across a frequency range
Okay.
to kind of find
Oh, where the
Your-
peaks are?
your resonant frequencies.
Right.
And from that, you can determine, well, it's kind of like finding where your structure breaks.
Yeah, that makes sense.
And then you could change it if you want to. Just the issue is like, right, you're always going to have a resonance frequency.
Right.
So you want to push it outside of the expected frequency limits,
Oh, okay.
which isn't always possible. So you want to like maybe move it to somewhere where the power is less, or maybe have a method that will, yeah, it's a, it's a big, I like to think basically everything I do in AlbertaSat is like juggling, right? You can't win. So you just got to get the best of the
Well, I mean,
combination.
you can win. It just takes a while. Like everything is dependent on one another. So you have this pit of oranges that you're digging into, and you're just throwing them up, and then you got like 7 in the air all at once.
It does feel more like a circus, yeah. But for the TVAC right now. Excuse me. So we Exalta 2 satellite did not fit in the TVAC.
Yeah, what happened there?
So, like a little bit of background. So you can imagine the TVAC kind of like, it's this big chamber. It's a big cylinder, basically.
Big bell.
With
big church
It
bell.
looks like a big bell, yeah. And the bottom of it is solid aluminum with this little like 4-legged thing on it. We call this stage.
Okay.
And that has the heating and cooling parts.
Right.
So the bottom has a saturated refrigerant chiller to stay at a constant temperature, like close to a constant temperature.
Right.
The top has a resistive heater for a like constant flux.
Okay.
And then the inside's hollow in a square shape. So you can take your square-shaped satellite, like back in kindergarten, and put it in the square-shaped hole.
That's awesome.
That was the idea. And so the TVAC was designed for Exalta 1, I believe.
Did Exalta 1 fit in it?
I don't think it was. It was made in 2021.
Oh, the TVAC?
Yeah.
Oh.
But it was designed with Exalta 1, which like Exalta 1 was already like out of the sky.
Deorbited, yeah.
Yeah. And so like the volume envelope it's kind of like a cross. So you have the corners of your satellite will touch the TVAC, and then in between the corners it will be air gaps. I mean vacuum gaps because it's a TVAC.
There's no air.
And so the idea is it touches the metal at the bottom, touches the metal at the top, and you can conduct heat through it.
Okay, that makes sense.
The cross section, however, did not match what we were designing for Exalta 2. So Exalta 2 was designed to what's called the NanoRacks CubeSat deployer volume envelope.
Yeah.
So NanoRacks, they're our launch company, or not launch company, or deployer company.
Yeah. Launch provider.
Launch provider, yeah. And they have a specified volume envelope that the satellite must fit in. For some reason, the TVAC did not match that volume envelope. And like by a millimeter.
Did we deploy NanoRacks for Exalta 1?
I do not remember. I don't think
I wasn't
so,
in the club then. So.
I don't think so. But yeah, I don't think so. But so the TVAC volume envelope is 1 millimeter off in every dimension, basically 1 millimeter, pretty close.
So what do you do then?
Well, you have to machine it out to be 1 millimeter bigger.
So you just take a mill off
Like
the
so,
mill, or?
in AINT, they go to put the satellite in, and the antennas are the part that stick out the farthest, and the solar panels. They're 1 mil too far out, and they just don't fit in the square hole. The square satellite did not fit in the square
satellite
hole.
did not fit in the square hole.
And so we are now working to take the TVAC apart, machine it so that it fits, and then assemble it back together, and then start testing.
You're just machining the stage though, right? Or is there like more to it?
Just the stage. We
Okay.
have plenty of room in the bell to do whatever we want. But it actually is like a bit of a balancing act, because the amount of heat you can conduct through a material is directly proportional to the surface area.
Yeah.
And in order to get the volume envelope to fit, we have to reduce our area by 25%.
And that's a lot of
That's a
lot
lot of
gone.
material.
Well, why is this change being made now? Like, are we going with deployables? Like
We're future-proofing the TVAC. We're designing it so that any NanoRacks launch vehicle or launch payload.
well,
right?
what if we're not going with NanoRacks though, right?
NanoRacks is pretty industry standard. In fact, they're a little bit bigger than industry standard.
Okay.
So anything that would fit in the NanoRacks deployer would fit in other deployers.
Gotcha.
But like the idea is we just future-proof it so that for Exalta 4 or whatever it's called, the next mission,
Yeah.
they go to TVAC test and it will fit in the set.
It would be cool if you had some like kind of vice.
So we're actually talking about adding something like that. So like if you reduce, so basically it's a plate on the bottom, a plate on the top.
Yeah.
And you think of it like you're squishing it down like you're making a satellite sandwich
Yeah.
in the TVAC. You have to, like, because there's tolerancing differences, you actually have to move that top plate down to squish it.
Okay.
And then you get a certain, like, you get a good contact area.
Right.
There's a bunch of different stuff that can happen. Like your thermal conductivity is proportional to the pressure at an interface. So the harder you squeeze down, the better your conductivity will be.
Right.
So I think we have to formalize that a bit going forward. But if you have to reduce the surface area on the top and bottom, what if you use the surface area on the sides of the rails? So you can add surface area there while reducing it elsewhere. And then you'd increase the conductivity while also having the envelope you want.
Yeah.
In order to do that, you would have to do the kind of squishing mechanism on the side so that you can like
How hard would that be though? I can't imagine.
We have some ideas, but the issue that arises is, well, there's kind of 2 points for the TVAC. Point number one is to validate the flight, or what would you call it? Like operations?
Operation conditions?
Yeah. So you're in the vacuum of space, you're getting a bunch of instant light, you're a PCB and you're generating heat because that's what you do.
That's what you do. That's your job.
And so there's a bunch of thermal transients going on, and you will see your satellite temp go from like 50 to -10.
All over the place.
That's a really big range. And so you want to ensure that in that range
You can
on
operate.
Earth that you won't fry something.
Yeah.
And so the TVAC needs to be able to heat and cool whatever's inside very quickly between that range. And to do that, you want the sides to be very conductive so that you can, if you're heating, the sides will conduct all the way around. And it's basically equivalent to heating on both sides. And so it's just faster because instead of going through in one direction, you go around in for both directions. That's for operations. If you want to test for validating a thermal model, you will then need to isolate the top and bottom plate. So you do not want any heat going around and outside. And so like that can be done by changing the side panels. Another reason why when validating is you want things to be known.
Right.
So you want the thermal conductivity through the top and bottom plates and the side plates to be predictable so that you can, when you have all the thermocouples hooked up and you see temperature gradients, you can then predict those using the known thermal resistances. So like that's why you want to isolate it so that you can just disregard those outside thermal resistances. But if you were to have a sliding mechanism with a sliding interface inside the TVAC, you're then introducing an asymmetry in your heat transfer.
Okay.
Because this side goes through a prismatic material, right? And this side now has to go through a sliced interface and then another material. So it's going to cause an asymmetry.
Right.
And it would make it harder to validate a thermal model.
And that's a big draw in using the TVAC.
Yeah. So yeah, balancing act.
Yeah, no kidding.
Do you want to increase the performance of it? And by performance, it's just like we'll reduce the time it takes to do a test. So like a thermal cycling test will take like 4 hours. If we reduce the surface area by 25%, we're looking closer to 5-6 hours. And so
that's a considerable amount of time.
Yeah. And so like we do want to make it feasible to test in the TVAC, but we don't want that to kind of, is it worth decreasing operation times to increase complexity? That's kind of the juggling act right now.
Yeah, that makes sense. Well,
What?
I need to make a thermal model for Iris, so
Right.
I'll need you and Ben's help on that one. I did just take what is that first Mechie 230 where
thermofluids?
Yeah.
Okay, yeah, that's basically all you need.
I was like when I first joined Alberta Set, I did the mechanical KOP and I did the SolidWorks part, and then I got to the LT Splice part, and I was like, oh, cool, I'm making a circuit. No, I was modeling a heat. Like I didn't understand it until I got to the second semester. I'm like,
The KOP.
what? This is crazy.
The KOP is literally the model that you have to make. That's the iris imager in that KOP.
Well, our iris is going to be most likely different.
Yeah, and it's probably going to produce a lot more heat.
Yeah, that's where sensor is going to. It's chunky.
What was it at the GAM? Where was it? Operating temperatures on Earth are like 50 degrees.
50 degrees Celsius.
And that's with convection. We might melt our satellite.
Yeah, so we're going to, well, that's with a module. It's not necessarily with, like, if we implement just the bare sensor, we have more control of the thermal management. But then we run into the issues of we're integrating hardware at the same time that we're developing, like, firmware for it, software that you need to work with it. And it's easier to, well, I shouldn't say easier, but, like, it's a little less difficult to integrate something that you already have like developed firmware for that is supplied by the manufacturer. So that's a big draw of using those modules. But 4 watts of power and like 50 degrees Celsius nominal, like not nominal, but like operating temp, like it just starts stacking up.
I think like what the work Max is doing for like the power budget. This isn't related anyway to what you're doing. This is for Exalta 2 power budget. I just thought it was so funny when he's like, yeah, we're going to need 7 solar panels for a sun synchronous orbit. And I like, it's just the, like, I just got the visual image of imagining 7 Hyperion solar panels wrapped around several times. But if Iris is taking 4 watts, well, that's going to be like 13. It's literally going to double it almost.
We'll see what happens. It's going to be interesting. I am a firm believer that when we have our system requirements, we're going to make leaps and bounds this summer.
Well, we can, like, I can technically make the mechanical requirements.
We
now.
have a list of iris requirements. It's just like a matter of, okay, what does everyone need? We need, like, it's hard to design like a PCB if you don't know A, what sensor you're using, B, what interfaces everyone else is using. You need to know like how the whole satellite's going to connect to one another. And not necessarily the whole satellite, but you need to know how does Iris or the Electra board or whatever we decide to name it this time, how does that interface with the onboard computer, OBC? Like how does that, right?
I'm about to say something really crazy. I think I've told you this already.
Maybe.
I want to put Iris in the middle of the 3 U's.
Yeah, actually, you know what? Well, that'll be interesting. I want to put it on one of the bottom or top U's, and I want to have it like, okay, I have to talk to Max about it still, but based on the way he was holding the satellite, we could just point out the bottom.
Yeah, and there are actually there's a lot of his flight
amount.
heritage where if you need like a longer imager, you orientate it in that direction.
Yeah.
I mean, that'd be fun. I think the issue, though, is like you'd have to probably go to a Dart-styled deployable.
Yeah.
And for some reason, everybody in this club hates Dart-styled deployables.
So much hate, man.
So, maybe hate's a strong word, but I went to Nikhil and I'm like, hey, can we make a Dart-styled satellite? And he's like, absolutely not. We will
no shot.
No shot. I think, though, it's a lot different. For mechanical requirements, it's literally be a box.
Be a good box.
Be a good box of a surface hardness of anodized aluminum 6061. That's it.
Well, and be a certain size and be a certain weight.
Be a certain box.
Be a specific box that must. What is my purpose?
We were a whole kilogram under the mass budget for Exalta 2.
Really?
Yeah, we can literally, like, we had a meeting to kind of discuss what the structure could look like for Exalta 3. And it's like, oh, we had a kilogram to play with, we can build whatever we want. Like, our structure is like 200 grams.
Hear me out. Propulsion system on a satellite.
I mean, they're not unheard of.
Oh, yeah. There's, I think, Nano Avionics has made one.
Is that cold gas thruster, I think?
That's the one we were looking at. I think it's probably cold gas, yeah.
I really, like, I wanted... Okay, here's the thing. We put a cold gas thruster on the satellite, and then what?
Bye-bye.
It's already bye-bye the second it opens up the doors during deployment.
I think it would be really cool to do solar sails and see if you can go from Leo to... just leave Leo and see if you can get to a higher Earth orbit.
I wonder. Interesting. Are solar sails directional, or like if you're heading away from the sun, they help you, but heading towards the sun, they hurt you?
Yeah, I think
that's just like my intuition. I don't know.
That would make sense. Yeah.
Or maybe there's only a reflective part on the one side, and you're
maybe
absorbing it.
Yeah. I don't know. We were gonna look into like solar sail deployments for CanRGX. That was one of our ideas that we were throwing around. But then we decided to do gecko adhesives. But I think solar sails. I have started doing more reading. I got a new book, two new books, and I've just been reading them. And I'm like, I miss reading so much.
Like rocket books?
No, they're not rocket books. I got Atomic Habits.
Dude, that book's so good.
It's amazing.
That's the only book I've ever read in one day. And like I demolished it in 5 hours.
It is so good. I'm like, I don't know.
Like I've never consumed a book so fast in my life.
I've only read it for like a couple of days, and I already feel like, okay, I can get my stuff together. And I'm like, I was at work today at 7 a.m. I can barely get out of bed normally at 7 a.m.
That is facts. I do text you some days. I'm like, where are you?
Yeah.
Oh, still sleeping. Never mind.
Yeah.
No, like that book probably. I read it last winter when I was living in residence. So like 2022.
Okay.
And like changed my life.
Yeah, it's really
so
good. And then another one I got. I have the subtle art of not giving. I'll censor it.
F word. I haven't read that one yet, but I heard it's really good.
I haven't read it yet because I want to finish Atomic Habits, and then I also have the Art of Thinking Clearly.
Oh, I know what you're talking about. I haven't read that one either.
Yeah, so I'll pass those down.
Right now I am reading Mastery by Robert Greene.
What is that about? Mastery?
Yeah, it's basically about how to become an expert.
That's awesome.
And like mentorship, like when it's like, yeah, it kind of like breaks down the certain role a mentor will fill at different points in your career. So like when you're fresh and brand new, you just find anyone who will talk to you.
Yeah. Yeah.
That's basically how it works, and just get taught. But then later in your career, it's more of a collaboration with your mentor, and stuff like that. Yeah, I think it's been great. I mean, I'm only a quarter of the way through it, but
dude, I love reading so much. I got those two books, and it's been like a catalyst for me. I'm like, my birthday's coming up. I'm like, I want to get this. I want to get this. And they're all books.
Oh, do you want to read Ignition?
I do, yeah.
All right, I'll send that your way.
Thank you.
It is pretty dense, though.
Well, I'm pretty dense, so.
It's pretty dense and pretty dark. Where
I like that style, though, where it's like, it's not, well, I guess, it's not taken with such a serious tone.
It's not serious, and he does say in the book, he's written in a way to scare you, because, the book is Ignition, History of Rocket Propellants, and talks about all liquid rocket propellants from the inception. And he goes on for like a hot minute about all the people in his, like close to him in his career who have just died because stuff's just blown up. Like he mentions this, when we're working with chlorine-based hypergolics, he always recommends a good pair of running shoes, because if it starts smoking, you have to get 500 feet away.
At least.
Something
At
like
least,
that.
Yeah.
Like you have to leave the facility a 1 mile radius.
Like that's terrifying.
But it doesn't stop me from wanting to actually build stuff.
Not at all, but
Propulsion team.
Yes, speaking of We got to get a jump start on that soon.
I
think it's going to be more of a fall thing, though, to be honest with you.
And I might not be here.
Well, it's something we can work on, though, like, still.
Yeah. I just need to, like, chill out from school. I say that, but I'm drowning this week. But I just need to chill out.
Drowning and still making a podcast.
Podcast is fun.
This is your break for the week.
Pretty much. I felt like I was banging my head against a wall for the last hour trying to figure out inverse fast Fourier transforms.
Ugh, that's not even school, though. That's...
No, that was for Alberta Sat.
Alberta Sat, yeah.
No, like, we're in sick, so I'm not going to work on school, even though nobody would like see me not working.
That's true, yeah.
So it's like, after this week, I have a midterm next week. We could just chillax, go to ice, get in a little cubby, and just chat.
Yeah, we should have a conversation with some of our advisors from Alberta Sat and see if they would be interested in helping us get this kind of rolling a bit.
I actually have already talked to people.
Oh, really? Who?
Yeah. Mike.
What did he say?
He said we will chat.
Oh, was that in ice last Thursday?
Oh, yeah, you were there.
Okay, yeah.
That was two Thursdays ago.
Yeah.
Yeah.
But I mean, like, an actual conversation, like, we should get this off the ground if possible.
Yeah, I do really want to do this, and I do think I will start neglecting, like, sleep to get this done.
Hey, man, I am on the 6-hour wavelength right now, and it's working.
Same here, actually.
I was getting 8 hours, and I was just exhausted. But 6 hours is perfect for me.
I did not sleep at all last night. Like, I'm almost at the point where I should just conceal the bags instead of trying to make them go away. Just cover them up, because, or just live with them.
Show up in a mask.
Like, it was like when I had that black eye a couple weeks ago. Yeah, I had a black eye. It was pretty nasty.
Yeah.
I went to a job interview with the nastiest black eye, and I looked like a thug.
It was pretty gnarly, yeah.
It was pretty bad. But, like, I had the black eye for 2 weeks. After week 1, when it faded a little bit, it blended in with my bags. And, like...
Honestly, yeah, after that, I
couldn't notice
really
it, but it was, like, still there. Yeah, maybe I'll try to get more sleep, get back on track.
It helps.
I feel like I say this every week.
You do. I think we all do.
Yeah. Well, Atomic Habits, what was it? Don't say you're someone who needs to sleep more. Say you're someone who will sleep 8 hours.
Yes. Yes. I am a person that will sleep 8 hours.
I am a person who will get up at 5 a.m. and work out and then still won't do it. But
hey,
it's who I want to be.
Exactly. It's about making an identity and then fake it till you make it.
I'm good at faking it.
You'll make it eventually.
Hell yeah. All right. 42 minutes. This is the longest one yet.
It is quite a chonker.
Alrighty. Peace out, Space Cadets.
See you next week.